In this video, we're going to take a look at projections in R2 and R3. So the two basic projections in R2 is projection onto the x-axis and projection onto the y-axis. Now I should point out that these projections are what are called orthogonal projections or perpendicular projections. You're going from whatever point you're at, you're projecting perpendicularly onto some line, okay, in this case the x-axis, or in this case the y-axis. The matrix which will accomplish this, let's do projection onto the x-axis. I can think of it in two different ways, right? I know that the point xy is going to be projected straight down, so the x-coordinate stays the same. The y-coordinate becomes a 0. So the first component of your result is 1 times x plus 0 times y. That would be the first row of the matrix. Likewise, the second component is 0, which is 0 times x plus 0 times y. So that would be second row. Or you can think of it, where does 1, 0 go to? Well, 1, 0 is this vector here. It's already on the x-axis, so it gets projected onto itself. That's the first column. And 0, 1 would be that vector, and it gets projected straight down to the origin, which would be 0, 0. So you can think of it either by rows, by looking at the formulas here, or you think of it by columns, by looking at where do E1 and E2 go. Likewise, projecting onto the y-axis, the x-coordinate becomes 0 and the y-coordinate stays the same. So, again, 0, 0, 0x plus 0y would be my first row, or 0x plus 1y, 0, 1 would be my second row. Looking at the columns, E1 gets projected to the origin, so 0, 0 is the first column. E2 gets projected to itself, so 0, 1 is the second column. Okay. Now, that's projection onto one of the axes. We could also project onto a line. So here we go down here. Sorry, those are lines. These are just an arbitrary line. And we will take a look at this both in terms of an angle or in terms of y equals mx, okay, like we did with reflections in the last video. So what I want to do is I want to say, okay, where does 1, 0 go to? So if this is the point 0, 1, I'm going to project perpendicularly onto that line. And what I'd like to know is, what are the coordinates? Well, I would get the coordinates by dropping a perpendicular. And so I could get the x-coordinate to here and the y-coordinate up to there if I knew the hypotenuse. Well, the thing is, I can get the hypotenuse because this first line I dropped was perpendicular. So there's a right triangle with a hypotenuse of 1 from here to there, because this was the point 1, 0, is 1. So this side length is the cosine of that angle. It's the adjacent side of the angle theta with a hypotenuse of 1. So now that I have this as cosine of theta, it becomes the hypotenuse for this right triangle, and the x-coordinate here is the hypotenuse times the cosine of the angle, so I end up with cosine squared. Likewise, that vertical side is the hypotenuse times the sine of the angle, so this would be sine theta, cosine theta. And so the matrix, the first column of the matrix, is the x-coordinate, cosine squared theta, times the y-coordinate, which is sine theta, cosine theta. Right? Now I have to do the same thing to get the second column with the point 0, 1. So take this, perpendicularly project down to there. I'm looking for the coordinates of this point. Well, if I knew that hypotenuse, I could then drop a perpendicular down here to get the x and y coordinates, because I know that this angle is theta. Well, I claim as well that this angle up here is theta. Notice that, well, this angle is pi over 2 minus theta, but this angle up here, well, this angle is pi over 2 minus theta, so this angle is pi over 2 minus pi over 2 minus theta, which is just theta. Right? So the thing is, I have a hypotenuse of 1, I have an angle of theta, this is the opposite side, so that hypotenuse has length, sine of theta. So when I drop a perpendicular, the x-coordinate now is going to be the hypotenuse times the cosine of the angle. So that's sine theta times cos theta. And the y-coordinate, this vertical side over here, is the hypotenuse times the sine of the angle. So that's now sine squared theta, sine theta times sine theta. And so there is the matrix that would be projection onto that line if you knew what the angle was. Okay. Now I want to change it up a little bit and say, well, what if I know the line not by the angle, but I know it by its equation, y equals mx. And in particular, just like the last one, m is the slope. M is rise over run, but that's also the tangent of this angle. So I know that the tangent of that angle theta is m, and I can draw this triangle and say if this is angle theta, make the opposite side m and the hypotenuse, not the hypotenuse, the adjacent side 1, so rise over run, or opposite over adjacent, is m. Tangent of that angle is m, and so then I can use Pythagoras to get this other side, 1 squared plus m squared, take the square root, and now I can see what's the sine of theta, what's the cosine of theta in terms of m. Right? So when I come back over here, I need cosine squared theta, but the cosine of theta is the adjacent side over the hypotenuse. It's 1 over that square root. So if I square it, it's 1 squared over 1 plus m squared, and the square root goes away. Sine theta times cosine theta, well, the sine theta is going to be m over that square root. The cosine is going to be 1 over that square root. And when I multiply them together, I'm going to get 1 times m on the top, which is going to be m. And I'm going to get the square root squared on the bottom here, so 1 plus m squared. Likewise, that'll be here, because that's the same thing, 1 plus m squared. And sine squared theta, sine of theta is opposite over hypotenuse, so m over that. So when I square that, I'll get m squared over 1 plus m squared. So this matrix is the matrix that I need for transformation, that is projection onto this line. You give me any point xy, I want to know where does it go when it gets projected. I'm just going to multiply it right here times xy, and I'll end up with these coordinates. Okay. Now, let's go to R3. Now, there's two types of projections in R3. There's projections onto a plane and there's projections onto a line. The book only does projections onto a plane, and that's what they are given here. They do 3 basic ones. That is projection onto the xy plane, in which case you drop straight down, which means the x and y coordinates stay the same, and the z coordinate just turns into a 0, right? So now I have 3 outputs. The first output is 1 times x plus 0 times y plus 0 times z. That's the 1, 0, 0. Or the second output is 0 times x plus 1 times y plus 0 times z. That's the 0, 1, 0 there. And the third output is 0, 0, 0, 0x plus 0y plus 0z. And that's what we get across here. Or you could think column-wise. You could say, where does 0, 1 go? Well, it's in the xy plane, so it goes, sorry, this is 1, 0, 0. It goes to 1, 0, 0. Right? Likewise, 0, 1, 0 is also in the xy plane, so it stays put. It goes to 0, 1, 0. 0, 0, 1, on the other hand, is pointing up here, and when you project it straight down, you get to the origin, so that goes to 0, 0, 0, and that's the third column. Okay. Likewise, orthogonal projection onto the xz plane. It's the y coordinate that's going to 0. And so I've got a 0 here and 1s there. Okay. Likewise, projecting down onto the onto the yz plane, it's the x that's going to 0. So there's a 0 there and 1s on that diagonal. Okay. So those are projections onto a plane. There's similar things where you project onto a line. So for instance, for this one, there's a corresponding, you could project this down on the xy plane, or you could project it back here onto the z-axis, in which case the point xyz is going to go to the point 0, 0, z. And the matrix I would get for that would be the first coordinate is 0x plus 0y times 0z, and the second one is 0x plus 0y times 0z, and the third one is 0x plus 0y times plus 1 times z. Okay, so that would be projection onto the z-axis. Okay. Again, you can also think in terms of where does 1, 0, 0 go? Well, it goes to 0, 0, 0. That's the first column. Where does 0, 1, 0 go? Well, it goes down to the origin, second column. And where does 0, 0, 1 go? Well, it's already on the z-axis, so it stays put at 0, 0, 1. And there's your projection onto a line, the z-axis. Right? Likewise, you could project onto the y-axis, which would look like this, where it's the y that's, so this would be projecting onto the y-axis down here. So that would go to 0, y, 0. And you'd have this matrix, or you could project onto the x-axis, which would get me down to here, which would be at x, 0, 0, and I'd have this. And it makes sense to me to see all these, 0 rows. I mean, the space I'm projecting onto is a one-dimensional thing, and so I would only expect to have one independent column or one independent row in the matrix that's doing this. Okay. Now, I also need to take a look at projections onto any line or any plane, but I think I'm going to do that in a separate video.